All right, so this video is made for organic chemistry students at Georgia Gwinnett College. Anytime we do an experiment in organic chemistry that involves a chemical reaction, two of the things that you need to do in your pre-lab are to write the balanced reaction and make a mole table. And so this is an example video of how to do those things. All right, so mole tables might look sort of weird and confusing at first, but they're really just basic stoichiometry. And so this isn't anything beyond what you learned in Chem 1. Now, to make this video, I didn't pick a reaction that we do at GGC. So instead, I took an experiment from the Boston University Open Libraries. But if you want to see the lab so you can see where I'm getting this information from, I've got a PDF on D2L, and then also here's a link to the website that hosts this experiment. All right, so in order to write the balanced reaction and mole table, you need to read the lab write-up. So you need to read the introduction and the procedure, and the balanced reaction is probably the easier of the two. In many labs, it may just have the balanced reaction written somewhere in the introduction, or maybe it describes the experiment in words, and then you need to translate that into the balanced reaction. For this example lab that we're doing, the reaction that they're doing is the reduction of fluorinone into fluorinol. And this balanced reaction is actually given in the introduction to the lab. The only difference is in the way it's written in the lab is the sodium borohydride is also written on the arrow. I've chosen to write it this way because that's going to make it easier to make our mole table, as we'll see in the next couple of slides. All right, so this would be the balanced reaction for this experiment. All right, so now what we need to do, once we know the balanced reaction, we have to look up through the procedure how much of the starting material are we going to use, how much of the reagents are we going to use, and in this case, methanol is the solvent. I also want to know how much of that we're going to use. And then we'll use the mole table to figure out how much of the product we're going to make. So I've pulled out the key statements in the procedure for this particular experiment that give us the values that we need, right? So I need to know how much fluorinone, sodium borohydride, and methanol. And so one of the partial sentences in the procedure is that we need to add 0.4 grams of fluorinone and dissolve it in 8 milliliters of methanol. So those are my amounts of the fluorinone and the methanol. And then elsewhere in the procedure, it says that we need to obtain 100 milligrams or 0.1 grams of sodium borohydride. So in these two statements, I have the amounts of the starting materials, and in this case, the methanol is the solvent that we need for this experiment. All right, so let's see how we're going to put this information into a mole table. All right, so this is an example of what the mole table would look like for this example experiment. And so the balanced reaction that we looked at before in the mole table should be written together in your lab notebook for the pre-lab. And so write the balanced reaction, write the mole table just below that, and then each column in the mole table corresponds to a different compound that's involved in the reaction. So I have my starting material, the reagents that are adding to it, the solvent, and the product. And then for each one of these four, I have a separate column in my mole table. All right, now this mole table is already partially and largely filled out. And so what I filled out is the information in the mole table that you can literally just look up. And so let's go through each of these. So the first thing we have is the names of each compound. I think that's self-explanatory. The row for the UTORP, this is the number that these compounds have in your UTORP. So this is going to be different probably for everybody. So in this example, right, I'm just assuming this is the first experiment we did, and so then these are the 1, 2, 3, 4 compounds in my hypothetical example UTORP. But these numbers would just be whatever UTORP numbers these compounds have in your UTORP. Then we have the CAS number, and again, the CAS number is just a unique identifier that's given to all compounds that are discovered. And so then you can just Google that. Is the easiest way to get the CAS numbers for things. Or sometimes even on our lab write-ups, they just give you the CAS numbers, and so you can just write them there. I'm going to skip this for a second. I'll come back to it. the mm, that's the molar mass, and the units are going to be in grams per mole. And so again, you can either calculate these based on the formula or just look up what are the molar masses of each one of the compounds. And then let me jump down to the last row. The density is only relevant for liquids. So since the fluorinone, the sodium borohydride, and the fluorinol are all solids, I didn't include their density, and I only included the density for the one liquid that we have at room temperature for this experiment, which is the methanol. All right, so I skipped the milligrams per milliliter, so let's come back to that. So this is the amount of that compound that you're going to use in the experiment, right? And so this is the information that we highlighted on the previous slide that we have to get out of the procedure. So the procedure said that we wanted 0.4 grams, and in the mole table, any masses I have are in milligrams, and so instead of 0.4 grams, I wrote 400 milligrams. And then the procedure said we needed 100 milligrams or 0.1 grams of sodium borohydride. So I wrote it as 100 milligrams of sodium borohydride. And then they told us that we needed 8 milliliters of methanol. And so for liquids, sometimes they'll give us the amounts in volume rather than mass. Now, if you notice for the molar mass, the units are always going to be grams per mole. So I didn't put units on each of the individual numbers. But for this row, if it's a solid, it's going to be in milligrams, or if it's a liquid, it's going to be in milliliters. So that's why I actually put the units here, because I don't necessarily, or right, we could have a mixture of solids and liquids. And then we don't know yet how much fluorinol, the product we're going to make. So that's why this is blank right now. Right, so everything I filled out are things that we can just look up, either from the internet in the various databases that you use to look up the information about the compounds we use, or in the case of the amounts, they're just given in the procedure. All right, so the only things we have to figure out in the mole table that we can't just look up are the moles, the mole ratio, and then in this case, since we're making a solid, the mass of the product that we're going to make. Okay, so and then I guess the other thing I should point out, we want to include the moles and the mole ratio for the compounds that are actually reacting or being produced in the reaction. And so methanol is just a solvent. It's not directly involved in the reaction. And so that's why I've written Na for the moles and the mole ratio, because it's not actually reacting, it's just serving as the solvent. But the fluorinone and the sodium borohydride are reagents. The fluorinol is the product, and so I need to figure out the moles and the mole ratios for those. Okay, so getting the moles is the easiest, right? To go from mass to moles, all I need to do is divide by the molar mass, which I already have in the mole table. So I'll show this calculation, and then I'll just give the result for this one. So to get the moles, I'm going to take the mass and divide that by the molar mass. So let me write it up here. So 400 milligrams is 0.4 grams. And then the molar mass is 180.19 grams per mole. So my grams cancel. And when I divide those out, I get 2.22 times 10 to the minus 3 moles of the fluorinone. So that's what I would put here in the moles row. All right, and then now we want to do the same thing for the sodium borohydride. And so I have the mass and the molar mass. So convert this to grams. So 0.1 grams divided by 37.83 grams per mole. That gives me 2.64 times 10 to the minus 3 moles. And again, let me point out, since all of the things in this row are going to be the units of moles, I don't need to put the individual units. They're all going to be in moles. Okay, so next let's think about the mole ratio. And so all the mole ratio is what we want to do is take whichever one of the reagents I have the least moles of and divide everything by that. Divide all the moles by that. So 2.22 times 10 to the minus 3 is less than 2.64 times 10 to the minus 3. So I'm going to divide both of these moles by this number. So obviously 2.22 times 10 to the minus 3 divided by itself is going to be 1. Nope. It's going to be 1. and then 2.64 times 10 to the minus 3 divided by 2.22 times 10 to the minus 3 gives me 1.19. Okay, so what is the purpose of determining the mole ratio? Well, it's to see what our limiting reagent is and to be sure our limiting reagent is what we want it to be. And so in this case, since the reaction, right, the stoichiometric coefficient here is understood to be a 1, right? I need 1 mole of that, right? I didn't write a number there, so it's understood to be 1 there, and I'm going to make 1 mole of product. So they're going to react in a 1-to-1 ratio. So that means whichever one of these I have the least of, that's going to be the limiting reagent. And so in that case, the limiting reagent is the fluorinone. And that's good. Generally, we want our organic substrate to be the limiting reagent, right? And then the reagents that we're adding to that, we typically want to be in excess. So we'll use all of this up and not waste any of our starting material. And so we want to be sure that the thing that we think should be the limiting reagent, in this case the fluorinone, does have the mole ratio of 1. And the other reagents should have mole ratios either equal to that, or oftentimes we'll make them a little bit higher to make sure that this runs out before the sodium borohydride. Okay, and then to figure out the mole ratio for the products, we just use the chemical stoichiometry, right? So this is the limiting reagent, and its molar ratio from the chemical reaction with the product is 1-to-1. So so the mole ratio between these two is the same. So this is going to be a 1. And so then however many moles of the fluorinone I'm starting with, that's how many moles of the fluorinol I should make. All right. And for organic reactions, obviously there are sometimes differences, but very often the stoichiometry is easy, right? It's usually 1-to-1-to-1, or at the very least, the reactants and products are often 1-to-1. Now, that's not always true, so you've got to be careful and be sure you check the reaction carefully, but it is not uncommon for that to be the case. All right, and so then the last thing we need to fill out in the mole table is the mass of our product, the fluorinol. So to do that, again, we'll just use the molar mass, only now we'll multiply. So I'll take 2.22 times 10 to the minus 3 moles, multiply that by the molar mass, and when I do that, I get 0.405 grams, but if I convert that into milligrams, it would be 405 milligrams. All right, and so most of the mole table, you'll just look up. The UTORP, just look it up. Cass number, just look it up. The amounts of the reagents and products, the amounts of reagents we would just look up from the procedure. The products we have to calculate. Molar masses, look them all up. Densities, look them all up, but again, we only care if they're liquids. So the only real calculations that we have to do, the only thing we have to figure out is the moles. And for the reagents, just divide the mass by the molar mass, and that'll give you the moles. Then for the reagents, whichever one you have the least of, divide all the moles of reagents by that, and that will give you the mole ratio. And so that can help us confirm, yes, the fluorinone is the limiting reagent, which is what we want. To determine the mole ratio of the products, use the stoichiometry from the reaction. So because it's 1-to-1 between the limiting reagent and the product, that's why the mole ratio here is 1. So then that tells us however many moles of fluorinone we started with, that's theoretically how many moles of fluorinol we should make. Then use the molar mass to convert the moles of the product into the mass of the product. And so another term for this, the mass of the product that we should theoretically make, in Gen Chem, we call this the theoretical yield. And so this is the theoretical yield of our product in this experiment. Okay, just a couple final notes specific to Lab G, which is often the first lab that we need to make a mole table for here at GGC. So in the procedure for Lab G, it talks about adding one equivalent of something. The term one equivalent is sort of short for 1 molar equivalent. So in Lab G, when it says to add, well, it really says to add 1 equivalent of pyridinium tribromide. What it really means is add 1 molar equivalent of pyridinium tribromide, right? So in that case, what it means is our reagent in this lab is E-stilbene. So however many moles of that you're supposed to start with, that's how many moles of pyridinium tribromide you need to add. So to figure what the mass of that is, right, calculate how many moles of E-stilbene you have. Since we want 1 equivalent of the pyridinium tribromide, we'll add the same number of moles of pyridinium tribromide and then just use the molar mass to get the mass of pyridinium tribromide that we need, right? And let's say a different procedure said to add 3 equivalents. Well, then we'd add 3 times the moles of whatever the starting material is. All right, and then just a final note on multi-step syntheses. Let me go to the next slide here. So here's our mole table that we just did and we filled it out. Let's say this mole table that we made was for the first step in a multi-step synthesis. Well, what that means is the product of this step would be the reagents for the next step. So the mass, if we were doing, let's say we were doing another reaction where we're going to use the product of this first reaction as the reactant for the new one, right? Then this is the amount of the fluorinol that we would use in that new mole table. And if you have a multi-step synthesis, you could make just one long mole table with all the steps in one table. What I might recommend, the more straightforward way to do it is to make a separate mole table for each step in the synthesis. But either way you want to do it is fine. All right, and so reach out to me if you have any questions about making mole tables before you have to do it for the first time.